So this is briefly a quick idea I have to 3D print stuff more efficiently with less energy and faster and higher quality. And that is, instead of using a 3D filament that is just plastic, which has some troubles when you print it, in that the plastic, you have to heat up to melt it to print it, but that heat can travel up the polymer string that you're printing, hurting the polymer above the thing. It can also lower the quality. It also means that heat controls have to be more precise, and that more heating means that also you might melt on the polymer below it. Then would somebody need to stick it together, but that could also make the polymer below it less strong and more creep and less accurate. So you want the heat to be as focused as possible. And it also means you waste energy heating up the other stuff. And also how fast you can heat up limits how fast you can print. So how would I solve this? Well, one way is we put in a lot of little metal nanoparticles, or we deposit metal directly into the polymer as we're growing it by reducing precursors to metal nanoparticles or metals. It's like metal salts, but we take off the cation or we take off the anion, not the cation, the negative part, by reducing agents. So like we turn copper chloride just to copper and chlorine comes off. Or somehow use electricity to do that, or reducing agent. But anyways, there's a bunch of little metal nanoparticles. Or you could also use carbon particles within the filament. And this has already been done with a bunch of filaments. These metal particles help in some ways to speed up. First of all, they make the whole filament more thermally conductive. So that means that we don't have to wait for the inside of the filament to heat up as much. And because it just conducts it. How much more thermally conductive? Well, metals are 10,000 to 100,000 times more thermally conductive, and good carbon insulations even more. Carbon nanoparticles are even more thermally conductive. So even if that's like a very little percentage of the total material, a huge increase in conductivity. So you really don't. So heating up becomes almost instantaneous if you heat up a part of it. The next one is to provide heat more locally where it needs to be dumped. And that would, I think, be done by these metal nanoparticles. Instead, we use them like a thermal heating element, like a resistor. Now, the most efficient way of heating off and stuff is you put electricity through something, and the resistivity of the material heats up it because the electrons hit the atom or hit the stuff in it. They can't move well, so some of the momentum of the electrons, instead of moves the atom, jingles it and heats it up. It's nearly 100% efficient, but usually this happens outside in the heating element, not directly inside the filament. But these metal nanoparticles can make the filament conductive enough that it doesn't straight up block electricity, but acts as a good thermal heater, what's more precisely a Joule heating. Joule, Joule, is how we say heating in this method. It's the simplest form of heating. This electricity, if you put one electrode here and another electrode here on opposite sides, a plus or minus, it goes through material along that cross section, so that little narrow path, and this mostly heats up that little narrow path. It doesn't want to spread very far. Electricity doesn't want to take a very long trip all the way from the top of the material back down or far away below it. So that means that the heat gets very localized heating, and now melt it. Plus, where it sparks more and heats up more is at the junction between metal particles near the plastic, which is what you're melting. You're not melting the metal. The metal is just like a sand or something mixed in with like a liquid, like water, like that you might, or cement paste, where you might add cement. So it also more locally heats up the plastic. There's also some other cool stuff you could potentially do with this design. You could, for example, potentially have metal nanoparticles catalyze reactions within the polymer, and because we often use metal nanoparticles to catalyze reaction polymer to make the material change its property after printing to make it much more stronger or thermally resistant after the printing. Metals could add extra strength in some ways to plastics. Some plastics, they could also make the polymer more thermally conductive in itself afterwards. It can make the polymer electrically conductive for something magnetic. You can make the polymer have more different types of colors or chromatic properties, such as making it shiny, or with the reverse, making it actually darker, because sometimes if you have metal nanoparticles of certain sizes, they can reflect light back and forth and kind of trap the light, making it darker. Different size metal nanoparticles have different colors, so you could have more color ones. Some metal nanoparticles like silver have antimicrobial properties, also copper. Then other ones that you could do with mixtures is that you could some metals are less toxic than plastics, some are more. Iron tends to be not very toxic one, magnesium, manganese. Copper is also not that toxic at low concentrations. The environment can absorb it and use it for stuff. Some ones are more toxic. Metals tend to be stronger, so you can make a stronger material. Not all metals, some metals. It's really complicated strength, and there's many different types of strength. There's strength for pulling, there's strength compression, there's strength that how much stuff that bends more and deflects more, and then stuff that just suddenly bursts. So there's many different types of strength. Strength to weight, strength to density, strength to volume. So it's more complicated than that. So I don't want to put it out as simple with how the metals could do. Another thing about the metals, printing this one, is metals thermally conduct heat faster, but that means also lose heat faster, which also can help set down print and print faster stuff and give you more accuracy. Another thing you could do with this technology to make it better is that you can add anisotropic properties, which I'll spell down here. Anisotropic. So anisotropic means that it doesn't act the same in all directions. And you could have metal nanoparticles that are different, that are more thermally conductive, make it more thermally conductive in one direction than another direction, which could even help 3D printing more. For example, if you had a long, thin thing, metal nanoparticle, which I'm just going to make as a really thick line, and then you had one on top of it, the metal nanoparticle would conduct heat lengthwise a lot faster than would conduct from one particle to another particle if they're stacked on top, because there's more polymer in there that's more of an insulator. And that can help make localized heating even more for 3D printing. But maybe you don't want that because you want something with metal nanoparticles giving you more isotropic property. But maybe you want an anisotropic property with conductivity or light reflecting, so you could do it so it looks different depending on the angle. That's another cool thing metal can do, is they can give you the iridescent look that looks different from different angles by reflecting light in different ways or scattering light into the rainbows. You can also make it more electrically conductive in some directions than other directions, have magnetic properties like that. You could tailor more mechanical properties more by having either you can have balls more of metal nanoparticles that make the whole thing looser and smooth more, or you can have more jagged ones that fit together more tightly and make the whole thing more rigid after printing. A bunch of things like that. Another thing is most plastics, when you print them, they're contracting and expanding, and metals can help reduce that contraction and expansion more, which would also make it a more precise way of printing everything out. Another great possibility with this technology, as I said, also carbon, which can theoretically be much stronger, but less but much stronger theoretically, but doesn't have as cool magnetic properties, but could theoretically be more conductive, but it needs to become a lot cheaper. But there's also other possibilities, like if you could burn away the plastic which we already do in some things with ceramics and stuff, you can have an all-metal piece. And you could use lasers to do this actually in the same chamber that precise, and use lasers to make more precise. But you could have a material that's both plastic and metal in different parts with the same filament, have different percentages plastic and metal by burning away some of the plastic. Or you heat up it locally more, so it's less plastic. That could give it, or if plastic has different material properties, depending on what temperature you print it, with some plastics too, because it can change the degree of polymerization, which can change the degree of how much everything is like cross-linked and connected to make it more rigid or less rigid, or it can make it, some chemicals, side reactions happen, and all those complex things. You could lead to a whole branch of new materials. The same is with carbon deposition. And if you really want to go fancy, you can mix in different types of nanoparticles for different properties. Iron is one of the most magnetic substances out there, but it's not the most, how would I say it? It's not the most thermally conductive electrically. That's copper. So you can have a copper-iron mixture of nanoparticles for different things. Copper is more bacteria resistant. You could also use this technology to make materials that are more chemically resistant, because metals are attacked by some chemicals more than plastics. So you could first print it out in this thing, and have the nice properties of metals inside, and then bury it in something that removes the metals that are just exposed. So the outside doesn't have any metals, but the inside has little tiny metal nanoparticles, pockets, throughout the whole entire thing. Or you could also try to reheat up parts of it now later on for mining, such as using magnetic induction or electrical ones. Another thing you could do with this whole thing that I'm just all thinking about this right now is you could have the whole thing is you could also use this to make metals that are more easily machined, because it's hard to machine something that is so as hard as metals and stuff like that, or that the heat can spread too much evenly throughout the metal. So first someone put in this, machine it for the very precise features, then heat up and solder it together into a more precise metal part. So the possibilities become really, really endless with this if we start thinking about it from the start, and not just as a metal on plastic one, but as a unique material. Well, thank you very much for listening. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours. The reason why I'm trying to do this is because then it starts getting monetized, and then I can devote more time to this and also make my own life easier with my disability. If you have any ideas for future videos, comments, or suggestions, please leave in the comment section below. Again, thank you very much. Goodbye.